Right. Good afternoon, everybody. It's my great pleasure to introduce our speaker today, Professor Rongomon Bordoloi from North Carolina State University, not too far from here. I've known Rongomon for a long time now. He did his undergrad in India, but he did his master's and PhD at the ETH, Zurich. After that, he was a postdoctoral researcher at the Space Telescope Science Institute in Baltimore. After that, he was a Hubble Fellow at MIT, and since 2019, he's been at NC State. He's now an associate professor there. He is an expert on galaxy evolution and gas and dust within galaxies, outside galaxies, how they interact with galaxies, etc. And today he'll be talking to us about that. He's done a lot of work using both the Hubble Space Telescope and James Webb Space Telescope, as well as other telescopes such as GBT telescope in radio. And so let's see what he has to say.
Thank you, Fresh. All right. Thank you again for inviting me here. It's my first time in South Carolina. I'm thoroughly enjoying the weather. I hope it's like this all year round. So before I start, I just want to get a show of hands. How many of you are undergrads? All right. I do have some target audience because you might be wondering, some of you might be wondering, what do these astronomers do, right? Just a disclaimer, I'm an observational astrophysicist. So what I'm going to talk today is observations of the hidden universe in baryons that I would claim drives galaxy evolution. That's a very big jargony words, but I want to start with something very simple. What do observers do when we go to a telescope? All right. So I wanted to show you a little time lapse, which actually we took, of on top of the Keck Observatory. You can see all the bubbling things here are actually clouds, and you can see the Milky Way rising at night. All the little flying things are actually planes going over, and if you look later carefully, there are even satellites going up in the air. Almost all of these are stars, and there are a few galaxies that you'll see. These are planes flying through, and throughout the night you're sitting on a telescope basically observing something, and if you have a camera outside, it'll take a really nice time lapse like this. And if I'm giving a public talk, I would like to say that that's what we do. We stare at the universe and try to figure out what the heck is going on. This is the moon rising, and again, this is a beautiful time lapse on top of Mauna Kea. And if you look at this image, it's spectacular, but it's still not as awe-inspiring as the next image I'll show you. Just for promotion, if you're an undergrad, you decide to go to grad school and study observational astronomy, this is the kind of cool stuff you get to do. This is the perk of the job, so to speak. And if you become a professional and you have the privilege of using some of the state-of-the-art instruments like the James Webb Space Telescope, you get to take an image like this. Some of you might recognize this image. This is one of the first images that Webb took, which was presented to the White House back in 2021, I think. And what it is actually a color image. That means in multiple bands, there are images of a galaxy cluster seen in the foreground. Okay, I can spend hours talking about this image. But for context, this total image is very deep. It took around 12.5 hours of Webb time to take. If you took the same image at the same depth with Hubble Space Telescope, it'll take you weeks. Okay, so that presented an exponential growth in capability with James Webb Space Telescope. These arcs you see are some of the most fantastic things in nature, called gravitational lensed arcs. Basically what's happening is there is a massive galaxy cluster in the foreground. You see these galaxies here. They are so massive, they reside in a massive dark matter halo, and it's so massive that it's spanning space-time. And as light is coming from some faraway galaxy, which looks like this, it's getting distorted as it reaches us, and when we see in projection, things look magnified and distorted, and you see these gravitational lensed arcs. It proves existence of dark matter, it proves that GR is right, and so on and so forth. That's great, but let's not focus on that. I want to ask you a question. How many galaxies do you think there is in this image? Anybody? 200. Good guess. Actually, it will be in tens of thousands in this tiny image. This image, if you want to see the size, it's like if you take a grain of sand, hold it like this, at this distance, the projected area you would see is the same size of the image that James Webb took. Okay, that's the projected area on the sky we're actually imaging. It's a tiny, tiny little pixel on the sky. But would it surprise you if I tell you that if you take all these galaxies, count out all the stars, all the dust, all the stellar remnants, okay, and do a total census of how much total baryons there is, you would only find around 13% of the total baryons in the universe. Okay, let that sink in. What I'm telling you is that more than 87% of the baryons, not dark matter, not dark energy, baryons, okay, standard model, particle physics model baryons, these are actually not seen in this image. So that is one of the big puzzles in modern day astronomy, which is called also the missing baryon problem. So
what do you call them?
So this we call it missing baryon problem.
Okay.
Okay. So the statement is basically that if you look at stars, supernova remnant, dust, and the ISM of galaxies, and sum it all up, it only represents around 13% of the total baryonic mass of the universe. 87% are actually not in this picture, not in starlight.
Why is it a paradox?
Sorry?
Why is it strange?
I'm trying to pose a question here. Like, where is it? It's strange because naively, not for an expert, naively you'd expect that, well, shouldn't we expect to see all the baryons that there is? But it's not there. So where could that be? So one question is it could be outside galaxies, right? And I want to show it by looking at a numerical simulation of a galaxy evolution. So this is from the illustrious TNG simulation. What you're shown here is actually an Andromeda-like galaxy forming over cosmic time. What we do here is actually, or the simulators do here, is actually take a large supercomputer and basically say that if you have dark matter distribution and baryonic distribution consistent with what the cosmic microwave background predicts, let it all evolve with gravity and solve Poisson equation for every time step and see what happens. Okay, then you say there are baryons there. If there are some density, stars will form, etc. The big image is showing you where all the gas is. This little image will show where all the stars are. This is again showing where the disk of the galaxy is. And this one is showing you a zoomed out image of what is the dark matter distribution. And we're going to start when the universe was like 1 billion years old and let it evolve. You can see initially there are very few stars and it's a mess. And you'd already see all the pink things. These are all the diffuse gas around galaxies are distributed all around the galaxies. Gas is accreting slowly through these cosmic webs onto the galaxy. As the galaxy is rotating, conservation of angular momentum means that the gas is actually falling in, forming a disk-like or rotating structure where stars are forming. And slowly, as time evolves, it will go away from this irregular thing to a more sort of settled, uniform disk-like galaxy that we understand. And the key here is that some of the gas is actually going out of the galaxy, some of the gas is actually falling into the galaxy. So there is a dynamic thing going on where supernova explosions or active galactic nuclei from the galaxy is actually kicking things out, falling back in, and forming stars. We're just rotating the image to show this a beautiful spiral galaxy. Forget about the color, it just shows where the heavy elements are in this simulation. But the point is, no matter what you do, if you want to form a beautiful disk-like galaxy, you start with a very morphologically disturbed object at very high redshift, let the gas fall in, which forms stars, then supernova ejects the gas comes out, falls back in, recycles and forms next generation of stars, and the process continues until a nice disk-like galaxy forms. This whole phenomena is to highlight a couple of things. Number one, that formation of a Milky Way-like galaxy does not happen in isolation. It's not a black box problem. Okay, there's a whole environment of gaseous, diffuse gaseous systems around it, which fuels the formation of stars in galaxy and helps the growth of stars in galaxies. Ergo, growth of solar system, etc., which happened like 4 or 5 billion years ago, happened in a system like this where gas accreting will form stars, stars will explode, recycle back, form next generation of stars where sun-like star can form and solar system can form where life can exist. Okay, what we're studying in broad stroke is trying to understand why we are here. Okay, what is our cosmic origin? That's the big theme. And the main point here is that to understand why we are here today, you have to understand how these cosmic ecosystems of diffuse gas can fall in and form stars. Yes.
What's the lifetime of a star? How long does it exist?
Excellent question. Depends on the mass.
Uh-huh.
So if you have a very massive star, it can last up to 10 mega years. If you have a very low mass star, that can last the whole time. Like there are stars that form, very low mass stars that form, that still are going today. Okay? Let's say 10 billion years ago a star formed.
So
it
they
can still
didn't
be
die
alive.
away.
They didn't die away. Not all stars die. First, the most massive stars die. They explode. They eject all the heavy elements. Then some of these elements go out, fall back in, and form next generation of stars. So this,
Question.
yes.
This movie that you showed us, how many lifetimes of a star does it last?
So that's a very good question. So the movie I showed, the time span is around 10 billion years. So if you have a series of massive stars, there will be 4, 5, 6 stars that form and die, etc. Right? Or maybe more actually. 10 stars that can form and die. Let's say a 7, 8 solar mass stars, 10 mega years. So 100 such stars would form and die in the time scale. But a small star can last throughout the movie. The point is, the fuel that's provided for these stars to form and die is coming from the extended environment around galaxy, which I highlight as the cosmic ecosystem. And if you want to understand how a galaxy actually forms, the physics of it, you want to constrain it, you have to understand these phenomena of how gas is ejected out of a galaxy, how it recycles back into the galaxy, and how accretion from outside the galaxy can actually help grow the mass of a galaxy. All right? Of course, this is my research area, so I would be very biased and tell you this is an important science question. Don't take my word for it. So in astronomy, every 10 years, all astronomers in the US actually come and form what is called a decadal survey, and that decides what are some of the most important questions that the community as a whole should study for the next 10 years, and what is the field where, most importantly, money should flow. All right? So there are 3 important fields that were identified by the 2020 Decadal Committee. One was to study worlds and sun and its context, that means study of exoplanets. The other one was to study multi-messenger astronomy, how gravitational waves actually can teach us about the structure of neutron stars, how we can combine it with different observation and study the intrinsically new field called the multi-messenger astronomy. And thirdly, the cosmic ecosystem, how amazing new observations and capabilities across the electromagnetic spectrum is redefining how we understand these massive gaseous halos around galaxies. Okay? And why is it so hard to observe? Like, sure, I told you that 87% of the gas is outside somewhere, which we only found out recently with high precision. But build a telescope and observe it. What's the big deal? The problem is, if you want to study something in, which is very faint, you need some sort of light source. Okay? So if you want to study these diffuse gaseous environments, they're so diffuse, their number density is around 10 to the minus 3 atoms per centimeter cube, that they just don't have enough self-gravity to collapse and form stars. If you don't have stars, you don't have nuclear fusion, that means you cannot emit photon. So effectively, they are dark. That's why they were hidden for so long. So there are tricks we can use to study, some of which Varsha uses here very effectively. For example, if there is a diffuse environment around the galaxy, I want to somehow quantify it. What if I find a very bright source in the background where a pencil beam of light is passing through to me? As the light is passing through, if there are, let's say, neutral hydrogen atom, okay, most abundant element in the universe. If there is neutral hydrogen atom and there is a photon which has which has an energy of around 13.6 eV, which is exactly the excitation energy of a Lyman alpha photon. So you can have a transition, Lyman alpha transition, which means that as the light comes to you, there will be lack of photon at 13.6 eV. By looking at this absorption of light in the spectra of the background source, we can quantify what is their kinematics, and try to understand and constrain this diffuse gas. Okay, this is a very powerful technique. We have known about it for 40-50 years now, called quasar absorption light spectroscopy. The other thing we can use, well, that's great. Quasars are very bright things in the universe. They are very bright. But what if we use the starlight in a galaxy itself? We can use the galaxy starlight itself as the background source and try to study what is in the foreground of the galaxy. That also, we can use the same trick and study what is going on when the gas is ejected from the galaxy. And studying the Doppler shift of the gas around the galaxy can inform you about something about what is going on in the immediate vicinity of the galaxy. We use that technique. And lastly, although I told you that you cannot image it, this has been a breakthrough in the last sort of 7, 8, 10 years. Although things are very diffuse, what might happen is that if there is a bright source nearby, photons from, let's say, a bright quasar or a bright galaxy can excite some diffuse gas around it, and that will emit a very faint emission around the galaxy. Very, very faint emission, which only the new generation of telescopes and instruments can pick up. And that allows you to actually image the diffuse gas around the galaxy. This has been a very recent phenomenon. Yes, sir?
I guess you started with the dark matter, so maybe you're moving to something else now, but out of this gas, and is that part of the dark matter, or gas is not a dark matter?
So, very good question. As I said, the talk is focusing on the baryonic matter, which is the missing 87% of the total baryonic content of the universe. Where these galaxies sit are inside massive dark matter halos, which provide a gravitational potential well, where in the center of which these galaxies and stars sit.
So the gas is the dark matter, right?
No. Gas is baryonic. Dark matter is some non-baryonic particle. We don't know what it is. It only interacts gravitationally. It does not interact electromagnetically. In this scenario, dark matters are massive gravitational potential wells.
Was that included into the simulation?
Yes. They are all starting with massive dark matter distribution, which we actually know very well from CMB. And yes, and then inside there, we allow the gas to actually cool down and form galaxies in the dark matter halos. There have been many Nobel Prizes awarded on the discovery and quantification of dark matter properties.
No, I'm sure they're
Yeah.
right.
So we do understand the dark matter distribution. We understand the cosmic microwave background very well, and that allows us to constrain the initial condition where the overall dark matter distribution of the universe is. So this is like the setup of what we want to study, and I will touch upon 3 things in this talk, which our group has worked over the last 10 years, and try to tell you a story of how these cosmic ecosystems form and evolve. I want to just set the scene, and I started saying that 87% of the baryonic mass is missing. So first I want to answer, where are they? That's one of the main reasons why the Hubble Space Telescope was built, just to highlight these are important questions. We want to then try to study a little bit farther away when the universe was forming stars very efficiently. We want to ask, how can galaxies in supernova explosions or AGN outflows, how can they get rid of the baryons from inside the galaxy so they can exist outside? And lastly, I want to go and use JWST and answer the question, when the first galaxies were forming, how actually they would assemble and form the first galaxies that we see today. Okay, how this system basically started. So if you chronologically reverse it, how these cosmic ecosystems were assembled, how you can actually chemically enrich these ecosystems, and where is the gas now. So I'm just going to go in reverse order from low redshift, that means very close to us, to high redshift, that means very early universe, very far away from us. Yes?
I think this is semantic questions. It's not really dark matter, but the baryonic matter that doesn't radiate in the radiation ranges that typically people have been watching. Is that correct?
Yes, when I say missing baryon, this is the baryonic matter which is not forming stars. Okay, and because there is no star forming, so they cannot
Less
emit
dense.
photons. Yeah, it's just less dense.
Excuse me?
Yes.
We're taught many times over that the baryons in total are 5% of the total
Mass.
mass,
Energy density of the universe.
energy density.
Yes.
Then how do we, where does that, from a big picture point of view, where does that 5% come from if 80% of that 5% is not visible?
Such an excellent question. So, where does it come from? So, this comes from the observation of the cosmic microwave background radiation. So, when the cosmic microwave background radiation formed, that means when the universe was expanding, it cooled down, and when the first neutral hydrogen atoms formed, basically it was very hot, so there are ionized protons which started capturing electrons and became neutral atoms. So one photon was free, right? And it has been free streaming when it happens till today. As it happened, it got redshifted to microwave, and when you observe it, you see a very beautiful pattern of an afterglow of the CMB, which is measured very accurately. When you do detailed analysis of it, you can actually quantify what is the total baryonic mass of the universe, what is the total dark matter mass of the universe, what is the curvature of the universe, etc., etc. And that tells you what should be that, because the Big Bang is the Big Bang, right? That created all the baryons we see today. So CMB, when it actually was created, has the footprint of all the baryons that ever existed. You cannot create more. So we know exactly how much total baryon there is in the universe relative to everything else from that observation alone. That's only one observation, but that's very profound.
Presumably the theory of the nucleosynthesis figures into the...
Nucleosynthesis tells you, yes, nucleosynthesis will tell you how different elements are created, like hydrogen, helium.
No, I'm thinking earlier.
Big Bang nucleosynthesis.
Pardon?
You're talking about Big Bang nucleosynthesis?
Yes.
Yes. In the first 3 minutes, we know from how we went from subatomic particle all the way to, let's say, hydrogen, helium, trace elements of lithium, etc. But that is all, that's all it is. That's all set in the CMB. So we can just measure the CMB that tells you what is the total mass of the baryons in the universe. So that is known very accurately.
And this 87% is the 87% of the 5% that.
Yes. So we get that total mass, 100. That's
Yes.
5% is there, and then you go today, do a census, count everything, and you find that only 13% are in stars, stellar eminence, etc. 87% is actually not in anything visible. So let's try to move along. So where are all the cosmic baryons today, right? And how do you do this experiment? I want to show the experimental setup because it's kind of tricky. So what we start is, you start with a census of a lot of galaxies, and you understand what is the property of the galaxy, you understand what is their, let's say, distance from Earth, what is their, how much mass they have, etc. So whatever you want, you can design an experiment to have a lot of bright background sources around these galaxies. Okay, these are called pencil beam sightlines using quasar absorption spectroscopy. Then you can ask nicely to a telescope time allocation committee, can I please use your telescope? And if you write a compelling proposal, you get to take a spectrum. This is, for example, an object which is the quasar spectrum of a using Hubble Space Telescope cosmic origin spectrograph. It looks something like this. Okay, it's just quasars are just supermassive black holes that are radiating a lot of energy. So they basically are some sort of deformed blackbody radiation. So their spectra look like power law. All the stuff in absorption is actually telling you what is along the line of sight. And because we know where the galaxy is, and the universe is expanding, and light moves at a finite speed, so all the, for example, neutral hydrogen you would expect around this galaxy would be redshifted from 1215 angstrom to somewhere another wavelength here. So for example, here I'm showing you neutral hydrogen around this object seen here, and triply ionized carbon around this object seen here. You can do it for different UV transitions because UV is very good for many atomic transitions, and you can do a census of all the gas that exists around this object. And of course, it's just one sightline. So you have to do it statistically. You do it around large sample of quasar galaxy pairs, and statistically build up a survey of what is the surface mass density of all the gas around these objects. Okay, and once you do it, you can start addressing this question of where are all the missing baryons in the universe. This is another way of phrasing that question. Okay, on the y-axis, I'm showing you total baryon to dark matter ratio. On the x-axis, I'm showing you what is the stellar mass of a galaxy. This line, dashed line, is telling you what is the total baryon to matter number density of the universe. Again, that's coming from the cosmic microwave background radiation. So if you're here, that means we account for all the missing baryons in the universe relative to dark matter. Okay, when you observe, you find something like this. Okay, so if you have a massive elliptical galaxy, you're missing a lot more gas than you'd find around a Milky Way-like galaxy. But even at the best case, you see that for a Milky Way-like galaxy, only 10 to 20% of the galaxy's baryons are in stars. For a dwarf galaxy, it's worse. For a massive galaxy, it's worse. And we're trying to find the question, what is happening in this phase space? Where is all the gas? Okay? Does that make sense?
Does this dark matter mean the baryonic non-glowing matter?
So omega, yes. Dark matter, baryons mean baryonic matter.
Yes.
Dark matter means non-baryonic
Okay,
matter.
so that term baryonic divided by dark is really non-baryonic.
So omega
gravitational
baryons,
matter.
it's a little technical. Omega baryon is the total energy density of baryons in the universe.
Okay.
Omega matter is the total matter density, dark matter plus baryons.
Okay, all right.
Okay, so I'm going to skip this slide. So this is just some of the results that you can find. For example, how the y-axis is effectively showing the surface mass density, proxy of surface mass density around galaxies. R is showing you, if you go away from the galaxy, how much of the mass exists. Forget about this part, focus here. This pie chart is really the census of what we found. So if you do a census, you find that around 15 to 20% of the gas around a Milky Way-like galaxy can be in stars and ISM. So the yellow part is solid measurement, and the blue part is basically showing you the limits given our models. Okay. Then we try to find around a Milky Way-like galaxy how much is there in hot gas. Hot gas meaning X-ray emitting hot gas, which is a 1,000,000 degree Kelvin plasma. So for a Milky Way-like galaxy, it's a very small fraction. Okay, it will change if you go to a very large galaxy. Then we looked at what fraction would you find in warm gas. Warm gas meaning 500,000, 600,000 Kelvin gas. Okay, it's a bigger fraction, around 5 to 30%. Then we looked at what fraction you'd find in cool gas outside galaxy. Okay, cool gas meaning again a 10,000 degree Kelvin gas traced by neutral hydrogen or any other neutron species. And that's a much bigger phase space. You can see it's going from around 30 to around 45%. Okay, note this this bar diagram is bigger than what is in stars and ISM. So there's more cool gas outside a galaxy than in the disk of the galaxy. That's the
What
key.
is ISM?
Interstellar medium. That means anything between stars.
What is blue and yellow?
Yeah, as I said, yellow means it's the floor. This is the lower, that's the minimum mass you have to have. And because there are model uncertainties on how much ionization corrections there could be or metallicity correction there could be, this is giving you what is the maximum there could be. So the true value would be somewhere between here. Okay, and the key point I'm trying to drive home is that if you look at this yellow diagram here and the yellow one here, there's more gas outside the galaxy than inside the disk of a galaxy. And if you count everything up again, we find that most of the baryons that we find in a Milky Way-like galaxy are not in the disk of the galaxy, rather outside of it. That's the key point here.
Isn't it paradoxical? In the hot case, yellow is smaller.
That's primarily because of the mass range we're probing.
Okay.
We're looking for a Milky Way-like galaxy. So the hot phase is set by what is the gravitational potential of the dark matter halo. If there is very hot gas, they will have high kinetic energy, they'll just escape the halo. So if you go to a larger dark matter halo, like a galaxy cluster, it has much stronger gravitational potential, so the hot gas cannot escape, so you'll find a lot of hot gas. So this is a statement about a Milky Way-like galaxy, that's why. So one of the big takeaways we make is that when you look at what is the total mass of a Milky Way-like galaxy, we find that the total mass basically is dominated by the gaseous halo around the galaxy, or the cosmic ecosystems dominate by mass the amount of baryons you'd see in a Milky Way-like galaxy. By the way, which is a good thing, because if we did not have such a cosmic ecosystems, the Milky Way galaxy will stop forming stars. It will become a red and dead galaxy very quickly. The fact that we have it means that we can explain why in the last 10 billion years Milky Way is continuously forming stars, because gases keep falling from this extended environment and keep forming stars over and over again. That's what keeps the Milky Way the way it is. Yes?
You consider gas only within the virial radius, or how it's like
Sorry, can you repeat that?
Do you consider, like when you are talking about the gas in the halo, you consider gas within virial radius, or where is the limit?
In this case, gas within virial radius. It's all gravitationally bound to the dark matter halo. So then, I want to move on a little bit and tell you, okay, I told you where the gas is. So is there a mechanism via which we can actually expel the gas out of the galaxies? So to do that, we're actually going to study a part of the universe when most of the stars of the universe were forming. So this is something called redshift 2 to 3. That means it's around 11 to 12 billion years ago. This is when most of the stars we see today were assembled first. And to study this, we have to zoom in a little bit and look at the galaxy itself. Some of you might recognize this image. This is the image of M82 galaxy, very close by. The white part is actually the stellar disk of the galaxy, and the red thing you see is actually outflows coming out of the galaxy, because there's a massive amount of this is called a starburst, basically a massive amount of supernova going off in the center of the galaxy, which is ejecting a huge amount of matter out in these radial directions. And this is seen, the red is actually H alpha, so it's ionized hydrogen gas that is seen, but it's a very complex system. You can see a lot of dust is getting kicked out. You can see a lot of X-ray gas. That means a lot of hot gas is getting kicked out. So it's a very complex phenomena, which allows you to tell that, locally we see there are these tiny dwarf galaxies, which are basically blowing out all of their interstellar medium. So perhaps this is a good mechanism that galaxies, one channel via which galaxies can eject a lot of their mass. This is good, but if you want to study these objects at high redshifts, or in the early universe, you have a little problem. The size of these galaxies look like this on the sky. Okay, they are tiny little dots. So if you want to study the details of what physics is actually driving these, like are they driven by momentum injected by a huge number of supernovas going on, or are they being ejected by a huge amount of radiation from massive stars, you cannot do it properly because things are tiny. So the trick we came up with is there's a faraway galaxy, is to use a gravitational lens galaxy, because gravitational lensing basically stretches a galaxy around, and it also allows you to do a spatially resolved study of little star clusters all around the galaxy. This was only possible because of new innovation of integral field spectroscopy. So a massive hardware project which basically allowed us to study, let's say, a field like this, such that if I take an image of this image, I'll have a spectrum of every little pixel you see here. That was a game changer, because before that, if I want to take a spectrum of everything here, it'll take me hundreds of hours. Now I can do a 100-fold efficient way. Just take 1 hour exposure of this field with an IFU. That allows you to take a spectrum of everything in there, and you're done. And you can do multiple science goals.
But I see the arcs are in blue, so not all the objects are produced, imaged as arcs. Only some that's at the correct distance that forms this arc.
So, good observation. Arcs are blue because basically an object which looked like this,
Yeah.
if you happen to align exactly at the right geometry, it gets lensed, and lensed not only distorts, it magnifies. So things which should appear red just appear. In this case, it happens to be a very blue object, highly star-forming object. So it will magnify. Even if object looks like this, it will appear bluer than it should.
But
in this
it's
case,
because it's accidentally in the right place.
it's just
Okay.
geometry. You will not get everything. Whenever you have a perfect alignment, you'll see
Okay.
it. This was work led by Ahmed, who is a postdoc here in his PhD. So the question we asked was, if you have a giant gravitational lens dart, by the way, this is the largest gravitational lens dart that exists in the universe, spanning a massive 38 arc seconds on the sky. And this is actually the counter arc on the opposite side. We're trying to ask the question, number one, can we image the extended emission that I talked about before? Like, if there's an outflowing gas coming towards us, there will be photons which will get backscattered by all the gas around and come towards us. So we wanted to see if there are gas which are resonantly if there are photons which are resonantly scattering in the galactic wind around these galaxies and coming towards us, can we quantify the spatial extent of the outflow? Okay, when I won't go into the detail, but I'll give you the punchline. When you look at it, you see this is where the starlight is, and these contours shown here is giving you the spatial extent of the outflowing gas around this galaxy. That tells you, number one, that yes, even at extremely high redshift, just like the picture of the M82, you see that galaxies are ejecting gas out of their stellar disk, okay, which is great. The second question we asked, okay, so that's great. What powers them? What is actually driving these outflows? And there, again, nature is our friend. So I told you gravitational lensing distorts an image. It also does something else. It magnifies different parts of the image at different rates, okay? And that allows you to basically use lensed object as a natural telescope and zoom in to the different part at different spatial resolution. So we did that, and forget the detail. What I'm showing here is on the y-axis basically what is the speed at which gas is being ejected, and particularly look at this blue area because I'm showing you what part of the galaxy we're sampling. Because of lensing geometry, I'm going to show you this blue area will be sampled over and over again, akin to using a microscope in a little piece of element and zooming in over and over again. Okay, you're looking at a 10x zoom, 100x zoom, 1000x zoom. That's what we're doing, which is again unprecedented. You could not do it 10 years ago. This is only possible because of lensing and IFUs. So if you go and zoom in 10x, there's more magnification. You go from sampling areas of a galaxy which have 25 to 30 kpc squared to around 10 to 5 kpc squared. All right? No, it's a 5x zoom. I was exaggerating. The next one is, if you zoom in even more, and you're starting to probe almost hundreds of parsec scale area. The key point here is that initially you saw an integrated value here. As you zoom in, you'll see that there's a huge spread in the speed at which outflows are ejected by different parts of the galaxy. And if you do detailed study, you would find that all these are very well correlated with where the local star clusters exist. So in this case, we find that when you have a lot of stars forming and supernovas exploding in local areas of a galaxy, this is where all the ejection happens. All right? So if I want to constrain my models of galaxy evolution, I have to actually go and ask the question, okay, what is the property of the local star cluster? If you have a lot of massive stars, you'll have a lot more outflow. If you have a lot of low mass stars, you'll not have a lot of outflows. So we're for the first time actually giving empirical constraints on how galactic outflows are being driven at cosmic blue.
Can you restate your statement? If there are a lot of stars, then outflow is more?
A lot of massive stars.
A lot of massive. That's counterintuitive. Doesn't the gravity pull things in?
You would think so, but the gravity is dominated by the huge gravitational potential well of the dark matter. So you have a lot of massive stars. Let's say you have 10 stars, which are 10 solar masses. Okay, they will last around 10 megayears. Then they will go supernova. So there are a massive number of type 1a supernova going on. And that energy is so strong that it's going to eject everything. That's the point. So the takeaway here is that outflows carry a lot of mass out of galaxies to the CGM, and it really depends on what is the local properties around the galaxies. So again, the argument is that you really need to study the stars to understand how they pollute the environment around galaxies. All right? Or enrich the galaxy.
This is actual image or simulation?
Oh, this is actual image. This is a fantastic image of the M82 galaxy.
Yes, it is.
In a supernova, what fraction of the mass is ejected versus remains in the remnant?
Locally, in this case, at least in our study, we found that at least 50% of the mass is kicked out of the galaxy. In a supernova, depends what environment it exists, but I think most of the mass is actually going out as neutrinos. In a supernova explosion, most of the energy is going out as neutrinos. It's like 99% of the energy. Whatever is left over is basically, these are shock waves which are sweeping up the interstellar medium around the supernova. That's what I mean, okay? When I say mass is being carried out, it's not the star's mass alone, it's the supernova shock wave carrying the interstellar medium with it and kicking it out of the galaxy. So the last thing I want to ask is, so we learned a little that most of the gases outside, they are being carried out by galactic outflows. So in the early universe, what happened? How do these things actually assemble? And I want to spend the last 15 minutes talking about our very interesting JWST work, where we did this experiment, where we basically went and found these massive, supermassive black holes in the early universe, which are very bright, called quasars. And we tried to study what is going on around them. And let's skip the detail. What we did is basically there are 6 fields. This is the first image I also showed, where we got some of the deepest JWST images ever found around quasars. So, for the undergrads in the field, please experts do not point out. Can you point out where is a quasar in this field? Quasar should be some star-like thing, okay? There are a bunch of star-like things here. Can you point out what could be a quasar in this field? And why? You're allowed to talk to your neighbor, discuss, and we'll discuss this. And there's no penalty, you can hazard a guess. Yes?
It should be some of the brightest spots.
Some of the brightest points? Which one? This one? This one?
Right in the middle.
Right in the middle? Why?
Well, that's the center of the picture.
Well, that's the center, but why is this a quasar? And why not, let's say, this guy?
Round spot.
Color. Color. You see, these are very blue, right? And this is fainter, but this is very red. So what happens when an object is very far away from us? Its light gets redshifted, so it appears redder. That's how we figured out that the universe is expanding. Everything gets redshifted. So in this case, when you take a quasar spectrum, it will look very, very red, just like this. That's why the color appears very red. So this is a fantastic image, which is 3 times larger than the deepest fields Hubble Space Telescope took. And it's deeper than the first image I showed you, but that's not what's exciting about it. The most exciting part as an observer, I can tell you, is because we have spectrum of every little dot that exists in this image. Because we use a trick called slitless grism spectroscopy. So what we did is, on the telescope, basically, as the light is coming, there is a grism, okay? Basically, think of it as a dispersion gradient, okay? And the light is coming, we just disperse it on the camera. So every single thing has a spectrum which is dispersed on the camera. We take an image.
And you can relate every spot with the stars that came out?
That's the cool part. I was going to show you that.
Okay.
You're too far advanced. So this is an image, okay? This is a color image zoomed in on a small part. You can see these are tiny little red things. These are big fat things. This is a star actually, and this is a crazy galaxy which is, undergoing some sort of interaction. So when you get the image after some processing, it looks like this, because this is what you'd expect. If you just take a bunch of light passing through a diffraction grating, it'll just disperse the light in all directions as a function of wavelength in this direction. These big fat things have very strong traces, so it's a mess. So the trick you have to do is, number one, know where your object is, and then subtract out all the continuum's traces you see here. When you do this, things appear much cleaner, like this. And by knowing, if you know where your object is, you can correlate this is the wavelength solution for this point, and this point. These are emission lines, O3 and H beta. So basically oxygen and hydrogen lines are emission lines are showing. Knowing this, you can figure out how far away this object is. This is an object at redshift 6. This another object at redshift 6. This object is actually from this object. This is Paschen alpha emission at low redshift. You can see how the galaxy is rotating and do a lot of fancy science. We're not going to talk about it. But by doing this systematically, you can build up a census of a large number of spectroscopic galaxies at very high redshift. This is the largest spectroscopic survey conducted by JWST at this redshift. And we have expanded it. It's not published, but we have around 2,000 galaxies for which we have confirmed redshifts. What can you do with it? Like, there's again, it's an hour's talk. I'm not going to go through it. Just wanted to show you. You see this clustering, like there are things in the same color shown. That tells you that galaxies are clustered around, preferentially around other galaxies, because galaxies don't live randomly in the universe. They cluster together, forming these overdensities of galaxies.
Galaxy ghettos.
Galaxy ghettos, you can call it. They will grow and eventually merge to form bigger and bigger galaxies. Okay. Eventually, these objects might end up becoming a Milky Way-like galaxies. Yes.
All quasars redshifted is a part of like the definition of what a quasar is?
Not necessarily. It depends where you're observing it, right? If there is a quasar in the Milky Way, it will not be redshifted, but we'll all be dead also. That's a different point. But if it is far away, because the universe is expanding, it will get redshifted.
So what is the meaning of the size?
The size here is actually not important. It's showing the O3 luminosity of these objects, where the most luminous objects are. The key point here is I just want to show that there is clustering of galaxies. You can do a lot of science with it. For example, it's a little technical. We're showing what is called a mass metallicity relationship. That means on this axis, we're showing what is the total metal content of this galaxy relative to solar, relative to the sun, what fraction of metals you see in these galaxies as a function of stellar mass. And this is a well-studied field where we know how mass metallicity behaves at different redshifts, and our objects are showing that at high redshift, there is already a mass metallicity relation. In other words, galaxies are already self-assembling via this outflow and accretion and recycling to say that more massive galaxies recycle more, so they form more stars, so they're chemically more enriched compared to low mass galaxies, which are more chemically pristine. All right? This is showing that already there's a lot of action going on. The other thing we can ask, and this is a little technical, again coming back to how the universe expands. This is redshift 6 and 7 is what is called the end of the epoch of reionization. So once the universe formed the first neutral atoms, all the universe was basically dark. There are no stars. So you only have neutral gas. Then the universe is basically opaque to radiation. So even if you have a good telescope, you won't see anything because it's dark. As the first stars formed, they started ionizing the environment around them, and universe became transparent, more and more transparent. And that process continued up to around redshift 6 when the universe became fully reionized. This is the last major phase transition in the history of the universe. So what we want to study here, this is, by the way, is a quasar spectrum, redshifted. The fact that you see nothing here in this part is called Gunn-Peterson trough, one of the predictions of the Big Bang theory, that there should be a more neutral gas at high redshift. This is exactly what we see. What we wanted to focus on are these little wiggles here. Okay? The question we are asking, in a neutral universe, why do you have these transmission spikes in Lyman alpha? If you have it, that tells you that these little galaxies that I showed are actually, when they're launching outflows or when they have strong, a lot of stars forming, they're basically creating a reionization bubble around them. And basically these bubbles are growing and growing and reionizing the whole universe. So the experiment we did was to do a cross correlation of where the galaxies are and where these transmission spikes are. And you just do a 2-point cross correlation between where the spikes are and where the galaxies are. If you do it, you get something like this. So at low redshift, when the universe is fully reionized, you get a profile which looks like this. basically at very close to the galaxy, because the density is very high, everything is opaque. But if you go outward, the UV background is so strong that everything is reionized. So it kind of goes to zero. But if you go to high redshift, okay, again, close to the galaxy is very dense, but if you go outward, there is this massive spike at a 5 to 10 co-moving megaparsec, depending on how you study. That can be translated to this picture. Basically, when the universe initially had first stars and galaxies assembled, you had these little reionization bubbles because galaxies are reionizing the environment around them. As they're growing, these bubbles will start overlapping with each other, and they will start growing, and eventually they will create a clear universe at the end of the reionization. These two curves are showing you these two images, basically. We're capturing what are the typical bubble sizes when the reionization is about to end, and we're showing you when the reionization ended. This transition takes around 100 mega years, not much. And that's one of the clearest signatures that reionization of the universe, the last major phase transition of the universe, is being dominated by a lot of little galaxies. They are not dominated by quasars. That was a debate for a long time. But they are dominated by a lot of little galaxies coming together, and all their weak radiation field is overlapping with each other and reionizing these massive ionizing bubbles. All right. Okay, I'm going to skip that. And I want to ask the question, okay, we now know that in the early universe there is this mass-metallicity relation that tells you there's a lot of chemical activity that's going on. We see that these galaxies are reionizing the environment around them. So A, they have a lot of hot stars. That means there is some sort of recycling is happening, forming a lot of new stars that is creating these bubbles. And we want to ask, like, can you see this? So again, we did the experiment we talked about before, and this is updated now with thousands of galaxies, where if you have a quasar here and you have another galaxy nearby, we're asking the question, at that rest frame of the galaxy, what do you see? Do you see a lot of neutral gas? Do you see a lot of ionized gas, etc.? So when we, okay, that's fine. So when we did this study, again, this is a little recent plot. This paper is not published yet, so bear with me. On the y-axis, again, this is a proxy for neutral gas surface mass density. Very loosely speaking, it's not technically correct, but this is what it's tracing. And the x-axis is showing you how far away from the galaxy you're actually probing. And what we find is that as you go away from the galaxy, actually the surface mass density of gas declines, but close to the galaxy, there's a lot of gas. Okay, it steeply climbs up. That tells you that, well, there's a strong correlation that when you have ejection, a lot of the more massive particles, or like more mass, is actually close to the galaxy, but smaller pockets of gas which are less massive are actually ejecting out to very, very far away. Okay, so we definitely see evidence of that. Secondly, we can do something very cool. We can look at the kinematics of the gas. Again, this is just a little too detailed, but what we're showing here is different absorption lines, again, with different kinematic structure. And we're asking the question, relative to where a galaxy is, how far away they are. Okay, that's a simple question we're asking. And we're putting it together in this figure. What I'm showing here on the x-axis is the gas we see, is it close to the galaxy and is it consistent with being within the virial radius? In other words, is it within the dark matter halo of the galaxy? Or on the y-axis, I'm asking, if it has a velocity, is it consistent with escaping from the dark matter halo of the galaxy? What we find is that for objects which are at lower redshift in our sample, are consistent, more consistent with being bound, and objects which are at the epoch of reionization, all of them are consistent with being unbound. All right? So what does it mean? That means as you go to higher redshift, you have these massive bubbles of reionization. At this phase, the galaxy's dark matter halos are very small. All right? So if you have a supernova going off, or 10 supernova going off, which is kicking gas out, they are kicked out with such high kinetic energy that the gravitational potential cannot bind them. They just escape the dark matter halo. So what happens? They will go out of this dark matter halo, for example, go into the IGM. As the universe evolved, these gas will move around. Eventually, perhaps, again, this is the speculation part, which is the fun part. Eventually, this gas can go and fall into another galaxy nearby. So, what you can have is metals, or in astronomy jargon, anything heavier than hydrogen, helium is metal, by the way. Any heavy element which is forming in one galaxy can go in and fall into a second galaxy and form stars in the other one. Right? Yes.
Do you see it in simulations?
Yes. There are fire simulations which actually did this prediction a couple of years ago. And this is, like, again, this is not a conclusive statement because this is still a little speculative. We still have to show that it goes and falls in there. But we're seeing evidence that it goes into the IGM. We know these things will eventually collapse, form a same object. So it stands to reason that things will go and fall into another galaxy. Okay? So imagine what I'm telling you. Okay? If it is completely true. Imagine what I'm telling you, the big picture concept. You and I, we're all made out of more than hydrogen and helium. We are made out of a lot of water. So there's a lot of carbon atoms, there's a lot of oxygen atom, right? So a lot of nitrogen in our atmosphere. All of these were inside stars once. So there is a really good chance that some of the atoms that you and I are made out of actually were formed in stars which existed in another galaxy, not in the Milky Way galaxy. Okay? This is one of the biggest lessons we're kind of approaching towards, that galaxies were massive. Galaxies are messy, I beg your pardon. They could form stars. The stars can explode as supernovae. The enriched material will go into the IGM, fall into another object, and form stars there.
Is that surprising?
Would you have expected 20 years ago? You can speculate, but we can actually show it, or starting to show it.
What's the time scale of matter being
such a good
from
question.
one galaxy and falling into another?
So, such a good question. Time scales are trickier. We know time scales of ejection. Time scales of ejection could be hundreds of megayears. You know, it's just at what speed are you coasting? And once you go outside the dark matter halo, you're expanding with the expansion of the universe. So things go much faster then. And if you go and fall into another galaxy within a couple of gigayears, so by the time our solar system forms from like these primitive galaxies, it evolves to becoming a solar system in a galaxy. That's enough time for this thing to happen. Yes?
So is this like using the materials are moving from one galaxy to another, right? So are they moving like shocks, or like do they form a bridge or some sort between galaxies?
So let me again give a caveat that this is speculative, right? I'm being a bit loose, but it's a bit speculative. So I cannot give you details. What we see is that things are escaping from the dark matter halo. Number two, there are these proto groups around these objects which will fall in and form bigger objects. That is absolutely correct. That's factually supported. The next step is my next logical step. What I'm making is the speculation that, well, these things can fall into a second proto-galaxy and form stars there, then merge and form from the Milky Way galaxy. So if they're in a IGM, they can be coasting with Hubble flow. They don't need to be in shock wave or anything like that. Okay.
Some of
Yes.
the ejecta could be just because of an AGN or something.
They could be
not star
dust.
formation.
They could be. That's a good question. The galaxies we study, I don't think they have AGN. Even if they do, the AGNs will not be strong enough yet. These are like their O3 and H beta lines are very very thin. These are not LRDs. So they might be dust, but again, I mean, you guys can answer it better. Like, it's hard to make sure dust survive for so long, right?
Right, no, regardless of the dust, the ejection may not be related to supernova and star formation.
At least the objects we studied, I think majority are supernova driven,
Okay.
or star formation driven, simply because they are too low mass to have AGNs.
Right.
But there will, of course, there's a massive AGN contribution. Like, I just don't have any quantification for that. As you go to lower and lower redshift, I think they become more and more important.
So the early universe, I mean, we always say that supernovae have a integrated energy into the ISM of 10 to the 52 percent, right? So this is a huge amount of energy that's
Yeah.
being ejected. So at the early universe, you have the galaxies that you're talking about. They're tiny proto-galaxies.
Yeah.
I mean, they're like hundreds of parsec, 1 kiloparsec around there, right?
Yeah.
And you have the same amount of energy that we see a supernovae in a late stage galaxy in a 200 parsec galaxy. So the energy that the supernova is ejecting is already enough. I think I agree with you.
Yeah.
So just like it's enough to push all this matter away from this very tiny galaxy.
Yeah.
So very small black hole, dark matter halos, and this matter can go to other galaxies that is very
Yes.
close by. And also the universe was very smaller, much smaller than now,
So
and more compact than
I-
now too.
I
so
agree.
yeah, it makes
There,
total
there's a
sense to
little
me.
there's a little trick there. You have to be careful. You have enough energy to eject it, but universe is very young. Do you have enough time for the gas to actually get that far out of the galaxy? So the stuff I see are
Depends.
already in the IGM, right? So it's not enough. If you just have a supernova going off, it's not enough. You don't have enough time for the gas to reach there. So what happens is supernova is needed to kick the gas out of the dark matter halo. Once you're in the Hubble flow, it's actually the Hubble flow that carries things. forward.
Exactly, yeah, in the filaments, in the common
It's
wave.
in the filament.
So
It's the
it
Hubble
can
flow
let
that's
go.
going.
Exactly,
Yes,
exactly.
yes. So that's a little caveat I have to add
Yeah,
there.
yeah.
All right. So I'm going over a little time, so I want to stop here. But the three things I want you to take away from this talk is that we have beautiful observational data that exists across cosmic time. And some of the major statements in the last 10 years we could make from it is that today the cosmic ecosystems around galaxies can outweigh the visible part of galaxies, right? And we think that feedback or some sort of energetic event in galaxies is strong enough to actually carry this material outside the galaxies, and they really depend on the local property of the galaxy that drives them. Young galaxies are very efficient in ejecting baryon out of their halos, and this gas chemically enriches the IGM, providing seeds for next generation of stars and galaxies. All right, with that, I'll stop today.
Thank you very much for an excellent talk. We've had many questions already, but yeah, any more?
Sorry, I actually have two questions. Well, the first one is a little more technical. It's just a data probably. Cosmic ecosystem today outweigh the visible part of galaxies. This is the first part that was about the missing baryon problem.
Yeah.
And you said that the missing baryon percent is about 60.
It's 83%.
Sorry, yeah, 83%. Okay. Is this number coming from? I guess that this number is coming from an average over a number of galaxies across different redshifts. What is the range of the redshifts, and what is the variance across of these numbers?
Yeah, so it actually, that's a technical question. That's a good question. I simplified it a lot here. So the missing baryon problem I stated is a very specific problem related to around a Milky Way-like galaxy. Why do we see so few baryons inside a Milky Way-like galaxy relative to cosmic abundance, right? If you go to high redshift, most of the missing baryon are probably in the IGM. Like you see it in the Lyman alpha forest. That's the dominant mass contribution. So in this case, the missing baryons are, how do we know they're missing in a local universe? There are massive surveys of galaxies, okay? There are massive surveys of galaxies with hundreds of millions of galaxies that were observed. So what you need to do is just compute what is called a stellar mass function, okay? And theory tells us very well what is the dark matter halo mass function. Compare the two. That's all you need to do. Immediately you know that they are not the same. The dip I showed, the curve I showed, is telling you where there is missing baryons already. And CMB tells you what should be the total omega baryon, where baryons are complete. So people did a lot of studies, especially in the late 90s, early 2000s, trying to do census of baryons. And one of the consensus was that, in the local universe, in the low redshift universe, baryons are still missing when you can actually count all the starlight very efficiently. And from theory, we always knew about it, but this was observationally shown like 20 years ago. And from that, one of the big questions we're trying to answer is like, where are they? And it took cosmic origin spectrograph to actually answer that question.
But then if you when you go to higher redshifts, you have a different percentage. Say that you have more missing baryons.
Yes.
Then the question is why do you, and this is almost a stupid question, but your second point was, well, we need to find a mechanism for galaxies to eject baryons, because this should be balanced. Why? If at higher redshifts you have a lower number of baryons inside the galaxy, maybe it's just the baryons are just accumulating over time inside the galaxy. You don't need an outflow.
Because the
mechanism.
Lyman alpha forest disappears. So at redshift 2, if you look at the quasar spectra I showed you, right? That's let me try to find it. The quasar spectrum I showed you, okay? There are so much neutral hydrogen there that you have nothing there. You don't see anything. If you go to lower and lower redshift, like it'll appear more and more like this. So if you go to from redshift 7 to go to redshift 4, it'll look like this. If you go to redshift 3, it'll be less. So that's called a Lyman alpha forest. So what's happening is a lot of the Lyman alpha is getting either reionized or they're going inside the galaxy. At redshift 2 to 3, when most of the stars in the universe formed, a lot of the IgM gas actually fell in. If you go to low redshift 1, Lyman alpha forest is very sparse. That's why we can have beautiful UV spectrum. Otherwise, you will have no UV observation. So baryons are no longer in the Lyman alpha forest, or most of the baryons are no longer in the Lyman alpha forest at redshift 0. That is true at redshift 2 to 3. So there's a huge transition. So we still have to figure out where are they.
Question about here.
Oh, sorry.
Probably a few slides down where you were showing the different, yes, this alignment. Do you have enough observations to tell between redshift 5.7 to 6.1 where you start seeing the change?
No, this is difficult. So when you do, there are several things here. This is, when you do this kind of study, there's a lot of cosmic variance.
Yeah.
Right? Sightline to sightline, there's a huge variation.
Right.
So when you try to combine all of it and make a general statement statistically, that you can do. But our numbers are still poor that we cannot do finer redshift bits.
Okay.
So our latest work, which I didn't show here, but same result, is actually expanding it to 6 fields. But there is another group, they have a much bigger sample, like that, 25 quasar fields. I think they would be able to make a much better statement about lower, finer redshift bins than we can.
To tell when the
Yeah.
redshift,
Yeah.
started.
Go back to the spectra. I'm confused how this emission lines you are seeing in the Gunn-Peterson trough. Like any emission there should be get absorbed.
So that's true. I'd call it transmission spike, but be careful. This is not emission. So what is being seen is here change in optical depth. Okay? Any absorption is e to the power minus tau. So when I change tau, it just means there is less absorption here. That's all. So any light you see is actually quasars intrinsic spectra leaking out, because these are like 2 Lyman alpha absorptions which are kind of like this. So transmission spikes are never emission, they are absorption troughs. Okay, just less absorption.
But my question is, even if there is like 0.1 neutral hydrogen after. Okay.
So this, all it means is that there are local ionization bubbles which are making sure there are more there are more ionized hydrogen than neutral hydrogen. That's why you're starting to see it.
My question is that if that transmission passes through the upcoming neutral hydrogen fraction or neutral IgM, doesn't that has to be suppressed by the neutral hydrogen after the transmission?
No, because it's redshifted. And you don't see evidence that this is indeed absorption. So the blue is Lyman alpha transmission, the green is Lyman beta transmission. Okay? If you have absorption, you would expect that Lyman alpha absorptions are deeper than Lyman beta absorption. This is exactly what you see. It's the opposite to emission. If it were emission, you'd expect blue should be stronger than green. That's why it's a little confusing, but it's a very important technical point that this is actually less absorption. That's what you see.
This is also why you have a blank region even in the lagging beta.
Exactly. Yeah.
Just like in the
Yes.
Yeah. And one more question. You said the dwarf galaxies are mainly doing the reionization.
So the statement is.
Not as much the quasars. Right?
So the statement we're making is that it's not one galaxy, but
Yeah,
it's the overdensity of galaxies, population of low mass population of galaxies basically that's doing the reionization. At least in our study, I think that's what dominating. There is of course a contribution from quasar, but I think this is at least our studies say that this is a very dominant phenomena at these redshifts.
Correct. But we know that there are also highly dusty galaxies, right? JWST is finding
Yeah.
very dusty galaxies. So if there is a dust shrouded AGN population,
It
could
might
it
just-
also make a
Yes.
contribution?
Yes. But I don't know what fraction of galaxies are dusty, honestly. That's still up for debate, right?
Uh-huh.
So do you have enough number density to
Well,
make it happen?
I know Enrique studies
Yeah.
these
It'll be interesting to see. yeah.
dusty star-forming galaxies, starburst galaxies. So,
So
yeah.
you know a fraction of faint galaxies that you missed.
Sorry?
Do you have a fraction of the faint galaxies
Oh.
that you don't see because they're
Fraction of faint gas. So we have a pretty well constrained O3 luminosity function. So we know our completeness up to O3 luminosity of 41.2, I think. We're very good up to that point. But of course, we're missing some fainter galaxies. That's a follow-up survey we're doing with H alpha that will tell us actually what fraction we did not see.
Do you see this size of the bubble, is it evolving or with the redshift, or is it?
It'll evolve with redshift because this is a Stromgren sphere, right? So basically, it'll just keep going at speed of light. So the sphere will just go bigger. Well, the intensity will reduce. It'll fall off r squared by r squared, but the radius will keep increasing until it starts overlapping with the others. If you go to high redshift, they're smaller. If you go to redshift 6-ish, they're bigger. And then if you go even lower, they're gone. There is no sphere. It's all reionized. So as I said, look up the paper by Matt McQuinn. They have these models. That's a simple model also, but they have the reionization bubble size, which probably will depend on, in your case, quasar luminosity, etc.
Any other questions? Yeah.
Your last slide, take-home message. So, young galaxy, is our galaxy Milky Way a young galaxy or old?
In my parlance, it's an old galaxy.
Really?
Because young galaxy is less than 1 billion years old. So these are objects at the epoch of reionization 13 billion years ago. So Milky Way is today, right? So it's already 13 billion years old.
I see.
So that's why I don't call it a young galaxy.
Okay, thank you.
It's still forming stars because you have this supply chain which keeps pumping gas in and it forms stars.
Very good job, yeah.
All right, anything else? No? Okay, let's thank our speaker one more time.